Hello, welcome to today's session. We'll be talking about centrifugal and centripetal forces. This will serve as a basis for us to build upon our next sessions, because the next sessions we're going to concentrate on balancing of rotating masses and then engine balancing. Now, as we can see on this board, there's a vehicle that is trying to negotiate or follow a circular path with a constant speed. Let's say that constant speed is v, or an angular velocity omega, which is in rad per second. Basically, you see people writing it just per second, the number of revolutions per second. Now, the vehicle must have a centripetal acceleration which should equal v squared over r, or omega square r, and must be directed towards the center over here. Centrifugal away from the center, if centripetal directed towards the center. Now, the car, according to Newton's second law, a force must act radially inwards towards the center for centripetal forces. For the car to be able to follow a circular path, it must have a force that will be acting towards the center. Unless this centripetal force is provided at all times, the car will not continue to follow that circular path, but will move forth tangentially to the circular path with uniform motion in a straight line, as shown here. You normally experience this centrifugal or centripetal force when you are in a car. So if a car is following a circular path and then you're negotiating the curve towards the right, you feel some sort of outward motion on your body. You feel like you are being thrown to your left or being pushed to your left. This force that you feel is what we call the centrifugal force. For us to continue, I want us to derive the centrifugal acceleration. You knew from Newton's second law that the sum of forces equal to the mass times the acceleration. Now, consider a car which was at, say, position A here, and then moved to position B. when it was at position A, it had the velocity vector v1, and when it moved to position B, it has the velocity vector v2. The radius to the instantaneous center of rotation, remember the vehicle is traveling in a circular path, so it's having some sort of instantaneous center for rotation, and then the radius to that center from the car is r. Theta is the angle between the velocity vector v1 and then velocity vector v2. Now, note that based on your geometry, you know the change in the velocity vector is equal to velocity vector 2 minus velocity vector 1. And this was as a result of drawing this vector triangle. So the change in velocity vector, which is from P to S, is basically traveling through this path, PQ and then QS. Please note that the triangle PQS, this triangle, and then AOB are similar. So triangle AOB and PQS are similar. AOB and then PQS, they are similar triangles. That being said, we can write the change in the velocity over AB to be equal to V over R. Then the AB is equal to the arc of AB, which gives us V change in T. That change in T is a short time interval that it takes the vehicle to move from point A to B through the circular path. So the change in V over V times the change in T will be equal to V over R, since we agreed that this triangle is similar to this. Hence, the change in V over change in T is equal to V squared over R. V squared over R basically will now be called the acceleration, because the change in V over change in T is acceleration. And this acceleration is what we are calling the centrifugal acceleration. Hence, we can say from Newton's second law, the sum of forces being equal to MA, the centrifugal force will be equal to the M times A subscript C, which is the mass of the vehicle times the centrifugal acceleration. Remember, we derived here that the centrifugal acceleration is equal to V squared over R. Now, knowing that V is equal to omega R, we can equally write the centrifugal force to be equal to mr omega squared. Alternatively, we can find that the centrifugal force by doing this analysis. If V is equal to d over t, which is distance over the time taken, then we can say that the t is equal to d over v. It's just basically changing the subject. Now, the D we are talking about is the circumferential distance. The D is the circumferential distance. Circumferential distance is a distance through one revolution. So that will be 2 pi r. Let's make that equation 1 here. Now, the frequency is 1 over the time period that it takes to complete one revolution. So we can still change that subject and make the time to be equal to 1 over the frequency. Now, knowing that equation 1 and 2 are basically representing the time, we can equate the 1 and 2 to get this. They make V the subject, then the V is equal to 2 pi r f. Again, from Newton's second law, we can agree that all the forces that will sum should be equal to the mass times the acceleration. So the centrifugal force will be equal to the mass times the acceleration, the centrifugal acceleration. Knowing the centrifugal acceleration to be equal to V squared over R, then we can write that the centrifugal force is equal to the mass times the velocity squared over R, which we derived before. Knowing that the velocity can be rewritten as this, then we just replace the value of V in this equation by 2 pi rf. Now, if we have a mass at the end of a light cord and we whirl that mass, which is attached to the light cord, around in a horizontal circle, we will experience a centripetal force by the inward pull of the cord. But from Newton's third law, where every action is equal to the opposite in magnitude and in direction, just the opposite in direction, we can say that the mass is exerting a radially outward pull on the cord of equal magnitude. So whilst the mass is trying to pull in this way, we are also pulling in this way. So the outward pull is what we call the centrifugal force and only exists as equal and opposite reaction to the centripetal force, as I said earlier. Now, it arises from the inertia of the mass or its resistance to the change in direction of its motion, represented by the centripetal acceleration. So the only difference between the centripetal and the centrifugal force is the direction. So if you write a centripetal, we can write this to be centripetal force to be equal to mr omega squared. Then the centrifugal force will be equal to negative mr omega squared, and vice versa. So if we have centripetal force to be a certain value which is positive, then the centrifugal force will be the negative of the centripetal. It's just change in direction. But in all cases, they have the same magnitude. Now, that is all for today. As I said earlier, this is going to serve as an underlying concept towards balancing of rotating masses and then engine balancing, which we'll be taking a look at next week. Thank you. Like, comment, and subscribe onto my YouTube channel so that you can receive notifications of new videos I'll be uploading.